Okay. Well, yeah, so Quiz Monday, probably on this stuff, 13.1 through 13.6. 13.6 is good. Let me do something here. You know, if you have this function f of xy equals 16 minus x squared minus y squared. Actually, I'm going to do something different here. Hang on. 16 minus x squared minus 4y squared. Yeah, that's a surface in 3D. I'm worried you might not know a whole lot about that surface, but I happen to know about it. But I might want to graph it. I might want to talk about it a little bit. Well, I'll tell you what. Do me a favor. Plug in the point 0, 0. Plug in the point 0, 0. What do you get when you plug in 0, 0? 16. Thank you very much. So here's the x-axis, the y-axis, the z-axis. Yeah, when you plug in 0, 0, you get a 16. I think that's the peak of this mountain. I think what we have here is a paraboloid, but it's an elliptical paraboloid, but it's upside down, pushed up 16. So at 0, 0, it's kind of at its max of 16, and then it's an upside down paraboloid. Now, so I can try to draw this here. It comes down like this. It comes down below here, actually, but I was going to sort of draw it here. And it's not circular. This one happens to be elliptical. I know that because of the different coefficients there. With the same coefficients, it'd be a very circular paraboloid. But this one is actually elliptical, even though my picture looks kind of circular. You know what? I'll tell you what. For one cool detail here, I'm trying to sketch this. One way to sketch it is, let's do this. Let's see what's happening when we let z equal 0. If we let z equal 0, then I'm in the xy plane. Let's see what that looks like. And then if z is 0, then it's this. And just to do some details here, I'll move the x squared, and I'll have x squared plus 4y squared equals 16. I'll actually divide by 16 is what I'll do, just because that's how I understand ellipses. If I divide by 16, I'll get x squared over 16 and y squared over 4 equals 1. So I know about ellipses. I know what this looks like a little more specifically here now. Let me see if I can improve my picture just a tad. Although we had the gist of it. We had the gist of it here. But what it's doing is it's, let's see, in the y-axis, it goes over from the origin 2 and negative 2. So 2 and negative 2 in the y direction. But in the x direction, it comes out 4 and negative 4. So it comes out 1, 2, 3, 4. And back 1, 2, 3, negative 4. So this is this particular paraboloid. It's coming down there. In the front, it's coming down here. On the side, it's going to hit there. On that side, it's going to hit there. Great. When it hits this xy plane, it is an ellipse there. Whatever. That's what this surface is. I don't know why I just spent some time drawing it for you and making you think about drawing it. What we're really trying to do is maybe at a certain point I can find a slope. Let's see. Let's try this question. Find the slope at the point 1, 1. In the direction of theta equals 45 degrees. Okay, you know, that is the truth. You know, what I got to do when I ask you about slope on one of these 3D surfaces, first of all, I got to give you a surface, okay? Then I got to tell you a point that I'm standing on. So then I'm standing on this point on the surface, and then I have to then there's a million slopes I can ask you about. That's what the last 2 days' lectures have been. I can ask you for the slope in that direction, that direction, that direction, that direction. I mean, so just because you're at a point doesn't mean, there's a lot of slopes at a point in 3D. So I'm asking for the slope in the direction of 45 degrees. What that means is from the positive x-axis, measured counterclockwise, that's a 45. So I'm asking for the slope in this direction. I'm standing on the point 1, 1. I could draw that. Where am I? I'm standing at the point 1, 1, but I'm up on the surface. So wherever that is, do me a favor. If you plug in a 1, 1, where are you? 9. Maybe 11. Maybe 11. 1, 1.
Yeah.
I'm at 11. So if I'm 1, 1, I'm at 11. I'm up right here. I'm on the edge of this surface. I'm on the edge of this mountain. Maybe a little higher. I'm at 11. At the point 1, 1, 11. But anyway, I'm at that point, and I am asking for the slope in... Well, I'm at that point. I'm asking for the slope in this 45 degree. I'm asking for the slope in this direction, kind of. Hey, look. If I think now that I've drawn this great picture, if you're standing on this mountain at the point 1, 1, 11, and you're looking in that direction, is that slope going to be positive or negative? If I'm standing on this point, 1, 1, 11, and I'm looking in that direction, I think that surface is falling in front of me big time, according to what that picture. If I'm looking in that direction. And by the way, if I turn around and look behind me, it's rising, toward the peak of the mountain. So behind me, the slope is positive, but looking in this direction, I believe that the answer is negative, and probably fairly steep. It looks like it's got a steeply negative slope. But we can calculate it. The way you calculate the slope is with the duff. I call it the duff, but it's really, it's called the directional derivative. The directional derivative. It's the slope in any direction. And like I said, this has been in the last 2 lectures. The formula for it is the partial derivative with respect to x times the x component of the unit vector that points in that direction, plus the partial derivative with respect to y times the y component of the unit vector in that direction. This little subscript u is the unit vector. Okay, well, I'm going to need some partial derivatives then. Let's get back over here. I want the partial derivative with respect to x, please. The partial derivative with respect to x, please. That's a pretty easy one. Negative 2x. I also need the partial derivative with respect to y. Negative 8y. I need these evaluated at the point 1, 1. Okay, if I'm at the point 1, 1, I plug in a 1 for x, I plug in a 1 for y, and I evaluate these, and I get these numbers. Negative 2, negative 8. Well, that makes me want to fill these in. Here I go. I'm calculating the duff at the point 1, 1, and I'm plugging it in here. That the partial derivative with respect to x was a negative 2. I have to multiply by the unit vector in the x direction. I'll get to that in a second. Plus the fy, which is a negative 8. And then I have to multiply by the unit vector in the y direction. Again, I've done this the last couple days, so this is not really new here. But when you're given an angle, how do you form a unit vector?
Cosine, sine.
That's it. Thank you. Thank you. When you're given an angle, the way you can form a unit vector is the cosine of that angle, comma, the sine of that angle. That is guaranteed to be a unit vector in that direction. So that's my u1 and u2 in this example. By the way, what is the cosine of 45? 1 over the square root of 2. What is the sine of 45? 1 over the square root of 2. So there's my unit vector. I filled in everything. This is a number. This is not a vector. This duff is a number. It's a slope. So it's a number. What is it? It's negative 2 over the square root of 2 plus negative 8 over the square root of 2. Cool. We could call it negative 10 over the square root of 2. I'm happy with that. Some people like to rationalize their denominator. That would create negative 10 square roots of 2 over 2 So then you might simplify it and call it -5 square roots of 2. That's the same number. It's approximately 7, -7, -7 point. -7.7. -7.07. All right, -7.1. -7.1. All right, so again, what does that mean? I'm on this mountain. I'm on the edge of this mountain. I'm at this point 1, 1, 11. I'm standing here on this mountain. I'm looking in this direction of 45 degrees, and the slope, it's falling in front of me at a rate of roughly -7. The mountain is falling in front of me at a rate of -7. If I stepped 1 unit in that direction, I would fall 7 units. You know, you could, however you want to say it. By the way, if I turn around and look behind me, what's the slope? It is. It's the exact opposite of that number. It's +5 square roots of 2, or +7.1 roughly. Yeah. If I look behind me. So, slope at a point. There's another idea, big idea from 13.6. That was one big idea in 13.6. The other big idea was the gradient. Let's just keep working with this problem. I'd like to find the gradient. The gradient is a vector. And it is this, and it is notated like this. Again, spent a couple days on this. And it is a vector, and here's what it is. It's the partial derivative with respect to x. In the x component, I'm going to call that -2x. And it's the partial derivative with respect to y in the y component. It happens to be -8y on this problem. So what I have here is the gradient at any point x, y. Well, okay, let's calculate the gradient at our point that we're at. We're standing at the point 1, 1. We would plug in our 1s and our 1s, which I've already done up there, and we would get these numbers, -2, -8. And it's a vector, and what does this vector do? It points in the direction of steepest slope. You know, when you are standing at this point, we just calculated this one slope. But I could calculate that slope, that slope, that slope, that slope. I could calculate a lot of slopes. This one is the direction of steepest slope. What does that mean? It means if I'm standing here and I look in this direction, -2 on the x, -8 on the y. If I look in that direction, that's the steepest slope in front of me. If I look in that direction. This is direction of steepest slope. Direction of max slope. The actual max slope is kind of interesting. The actual max slope is his magnitude.
I got 8.24.
That's his magnitude? 64 plus 4, square root of 68, 8.24. Okay. Yeah, his magnitude is actually the square root of 68, or approximately 8.24. Okay.
Yeah.
All right. Cool. That's the max slope. Hey, remember when I was looking in this 45-degree angle direction? The slope was -7, and then behind me was +7. Anyway, that +7 slope was sort of close to the max slope, and then that behind me direction was sort of close to that direction. You know, it wasn't that direction. It wasn't, but behind me, if that's 45 degrees, then it's 135 degrees. 135 degrees, the slope was 7. This is close to that. I don't know what it is, but it's close, and it's the max slope at about 8.2 in that direction. You know the other thing? The last thing, just to make another connection here, same problem. The last little idea connecting these thoughts is that the gradient is the gradient is normal to the level curves of the function. The gradient is normal, which is perpendicular, to the level curves of the function. I wonder if I can illustrate all this at this point. Let me think this through here a second. I mean, let's see. I think I want to sketch the level curve that contains this point 1, 1. I'm working at this point 1, 1. Now, we said this a second ago. When you are at the point 1, 1, what was your z value? 11. So that means, watch, I want to sketch the level curve. I want to sketch the level curve when c equals 11. It's called the level curve. It's called the contour line when c equals 11. If you remember doing that in 13.1, what we would do is when c is 11, that really means z is 11. You would plug 11 in for z, and you would go ahead and now try to sketch the resulting curve. All right, you guys, this ain't going to be the prettiest thing in the world. Let me see. If I move this x squared and y squared over here, because it's elliptical, it's not a circle. You see what I just did? I moved my x squared and my y squared over here. I subtracted the 11 here, but the truth is it's an ellipse, and I only understand ellipses if I divide by 5, divide by 5, divide by 5. Let me see if I can do that. And then the truth is, I want that numerator to have a coefficient of 1, so I'm going to do another little fancy move. I'm going to multiply by 1/4 and 1/4 here. So here it comes in a different form. I have x squared over 5, and I have y squared over 5/4 equals 1. That's the ellipse that occurs at c equals 11 or z equals 11. Here's a picture of it, sort of. But it's the level curve, which we don't draw up there on the surface. A level curve, we draw it down in the 2D XY plane. So I can try to draw this. I want to try to draw it. Let me try. In the XY plane, I have an ellipse, and I'm trying to draw here. In the x-axis, I should go over the square root of 5, which is roughly 2.3-ish. The square root of 5, and back this way, the square root of 5. On the y-axis, I should go up and down the square root of 5/4. What's the square root of 5/4?
1.11.
1.11, thank you. So that means I'm going to go up 1.11 and down 1.11. Okay, cool. I think this is my ellipse. That wasn't too bad. Now, where am I on this ellipse? Now, by the way, this ellipse is the contour line or the level curve for good old c equals 11. That's what it was. So really, it's up there at a height of c equals 11. I'm looking down on it, and that's what it looks like when I look down on it. And I'm at the point 1, 1. You know, the point 1, 1 is on this ellipse. The point 1, 1 had a z value of 11. So the point 1, 1 is right there. It's on the ellipse right there. And I'm at that point, and I want to sketch the gradient. Where the hell's my gradient? At this point. My gradient at this point is -2, -8. When I sketch this, it should look like it's perpendicular to this level curve. Let me see what happens. -2, -8. Okay. Great. Well, oops. Now, does it look like it's perpendicular to that ellipse?
Yeah.
It does, kind of. The ellipse could have been a little more curvy right there. But yeah, Yeah, that's what's supposed to happen. That the gradient is this vector, and it is perpendicular to the level curves. And it sort of looks like it is. I tried to be kind of accurate. The gradient is perpendicular to the level curves. It's pointing to the steepest part of this mountain at this point. Okay. All right. Now, that's good stuff, you know. I think I'm going to try to move on into 13.7. And to move on into 13.7, we need these kind of ideas. Don't forget this. The gradient is normal to the level curves. Actually, this is just... All right. Okay, I'm trying to ease into 13.7. This is one of the hardest things to explain, to tell you the truth. I usually do a good job. I've been doing it for years. I'm going to do a good job today. But I got to gather my thoughts here. This is tricky to explain. I could not explain it. I could just tell you, hey, robots, follow what I do, robots. Or I can try to explain it. Here's what I want you to see here, okay? When we have this f of xy, we know it equals z, and we know what we have is a 3D surface. Okay, cool. We know that. All right. We know that when we sketch its level curves, we plug in a number, we plug in a c value for z, so now there's a number there, and then we do, but now, this is, when we do that, it's a 2D level curve. I mean, a 3D surface has a 2D level curve. Okay. When we calculate the gradient, we know that the gradient is an fx and an fy, and it's a 2D vector. It's a two-dimensional vector. And what we just got done saying is it's normal to the level curves. We can sketch this in the xy plane, and it's normal to the 2D level curves. The 2D vector, just like that example, is normal to the 2D level curves of this 3D surface. Okay, cool. That's not bad. Now, here's what's new. What's new is, if I have a 3D, a function of three variables equals a fourth variable. Okay, we haven't worked with that much, but it was introduced originally in this chapter. Okay, now that's a 4-variable situation. Okay, so this is a 4-dimensional surface. You cannot really imagine a 4-dimensional surface, but it exists. I mean, the math exists. So it's surface might even be a bad word. It's a 4-dimensional thing, all right? Now, hang on. If we put a C value in there, like a C value, and let me just, like a C value of 0, but it could be any C value, but like a 2 or an 11 or whatever. But if we put a C value in there, now, okay, hang on. The analogy is, I'm doing this analogy here. So the analogy is, it equals 0, but, oh, Jesus. We plugged in a number for the fourth variable, and so we have, this is a 3-variable situation. And so the level curve is not a level curve, it's a level surface. It's a 4D thing, but now I get a 3D level surface. Are you following me? Is that okay? It's this this one dimension down analogy here. So in a 4D thing, when you plug in a number for W, you get a 3D level surface, which you can draw a 3D surface. And if you calculate his gradient, it's a 3D vector, and I want to change the damn letter. Okay, I'm just going to say this. When we calculate his gradient, we would calculate this, and it would be a 3D vector, fx, fy, fz. It would be a 3D vector, and it would be, remember this guy was normal to the level curves, normal to the level curve, which meant there's a level curve and the gradient is normal to the level curve in 2D. This 3D gradient, this is a different kind of gradient. It's a 3D gradient. I mean, I'm up a level, and so it's a 3D vector, and it's normal to the level surface. It's normal to the level surface. So a level surface might be is a 3D thing here. So it might be a sphere or something like that. It's a level surface, and then this 3D vector would be normal to the level surface. It would be normal to the level surface. This 3D gradient. 3D gradient is normal to the level surface of a 4D thing. Jeez, spit all this out. Right. A 4D thing has a 3D level surface. That 3D gradient is normal to the 3D level surface of the four-dimensional object. Right, right. Good, that's not bad. Now here's the deal. See, here's what we're getting at. What I'm going to try to do is I'm going to try to find the equation of a tangent plane. That's where I'm headed. I'm trying to head into 13.7. And in 13.7, I'm looking for the equation of a tangent plane. And that means you have to go back to chapter 11 and try to remember planes just a little bit. But maybe one of the things you remember about when you try to find the equation of a plane, you needed a normal vector. Do you remember that? If I wanted the equation of this plane, I needed to fill in the equation, I needed a normal vector to my plane. I need a normal vector to my plane. So if I'm looking for a tangent plane to this surface, what I need is this, I need this normal vector. I need this thing that's normal to the surface. I need this thing called the 3D gradient. Not the old 2D gradient, not this. So this is cool and useful for its purposes. This is cool and useful basically for this purpose. The equation of the tangent plane, it's normal to the surface. Maybe for some other purposes coming up. But see, what's weird is that okay, here we go. All right, so this ain't the equation of a tangent plane. This is just some surface. You know, this is a surface, right? Look at it. It's a 3D surface. Do you even know what it is? Maybe you know what it is. What is it? It is a sphere, centered at the origin, radius 3. Right, this is a sphere centered at the origin, radius 3. So it's a 3D surface. All right, now watch what I do. I move this 9 over. And so I set it equal to 0. If I move the 9 over, it's equal to 0. But then what I do, this is a trip now, what I do is I pretend for a second that this is, now that it's equal to 0, I'm going to label it like this. So now that it's equal to 0, it's got all the x's, y's, and z's all on one side. It's all a big expression, and I'm going to call it big capital F of x, y, and z. Now, when I call something a function of 3 variables, that implies that it equals a 4th variable. But I'm lying. I'm cheating and I'm lying. Hold on now. Okay, so for a minute, pretend it does. Pretend it equals a 4th variable. But the truth is, what am I about to do to that 4th variable? What does it really equal, please? What does this really equal? It equals 0. Thank you. So what I really do is it's not really a 4 variable situation. It's a 3 variable situation. I'm pretending that it equals w just for a second, but then I'm plugging in a 0 for w. So it equals 0. So it's a 3D surface, but I'm pretending it's the 3D level surface of a 4D thing. It's a 3D surface, but I'm pretending that I got it from some 4D thing and I plugged in a 0 for w. But when I use capital F, it means it equals 0. So it does not, when I use a capital F of x, y, and z, it's not really equal to w, it equals 0. But I'm pretending it's the level surface at c equals 0. And so his 3D gradient will be normal to the surface. Jeez, maybe I did explain that good. His 3D gradient, which is this capital F, the capital F is the right notation, is a 3D gradient, capital F, subscript x, capital F with respect to y, capital F with respect to z. It's a 3D gradient, and it is normal to the surface. It is normal to the surface f of x, y, z equal to 0. So it serves as it's normal, then I can say it's normal to my tangent plane. And I use this as my normal vector to the tangent plane. This new 3D gradient called capital F. Damn, that wasn't too bad of an explanation, maybe. Maybe. So here's the equation of a tangent plane. Here's the equation of a tangent plane is this. Here, the equation of a tangent plane in 13.7 is the equation of a tangent plane is this. You might remember it was, okay, don't write this down. Back in the day, the equation of a plane was A, don't write this down, x minus x naught, B, y minus y naught, and Z minus Z naught, and maybe equals 0. And maybe you remember that the ABC was my normal vector, ABC. Well, instead of the ABC, what's my new normal vector? My new normal vector is the 3D gradient using the capital F notation. So the equation of a tangent plane is capital F partial derivative with respect to x, capital F with respect to y, capital F with respect to z. My vector, my 3D gradient, is normal to the tangent plane. And again, when we use the capital F notation, what are we talking about? It's still a 3D thing, but it's sort of disguised. It's capital F of x, y, and z, but the reason it's still a 3D thing is because it doesn't equal w, it equals 0. There's only 3 variables here. Cool. Maybe I explained that. Whew. It was tough. Let's do a problem. Let's do a problem. find the equation of the tangent plane. Find the equation of the tangent plane to this. Watch this, watch this, watch this. F of x, y equals 3x squared y minus 2xy. At the point 3, 2, 42. All right, you guys, this is pretty cool. I want the equation of the tangent plane. All right, you ready? Here's what we do. If I want the equation of the tangent plane, this is my formula. If this is my formula, I need this 3D gradient. I need this capital F gradient. Well, if I'm going to do a capital F gradient, I think the first thing I need is capital F. What the hell is capital F? Capital F is what you have when you get all your x, y's, and z's on one side equal to 0. What do I have right now? I have z equals 3x squared y minus 2xy. That is what that is. So how do I make this a capital F? Move the z over. Thank you. You move that z over, and it equals 0. But I'm not going to say it equals 0. Now I'm going to call it big capital F is what I'm going to call it. Right. Awesome. And now I need big capital F, partial derivative with respect to x. I need big capital F, partial derivative with respect to y. I need big capital F, partial derivative with respect to z. Cool. Let's do it. With respect to x. With respect to x. 6xy. 2y. Good job. Okay, with respect to y. 3x squared minus 2x. Good. With respect to z.
1.
Actually,
-1.
-1. Dude, we got it. Let's do, let's evaluate these at the point. We are at the point 3, 2, 42. So if any x's we see, we should plug in a 3. Any y's we see, we should plug in a 2. Any z's we see, we should plug in a 42. I don't have any z's, but here I go. Plugging in that 3 and that 2 for x and y is going to give me some numbers here. This number is going to be a -1. Let's see, plugging in the 3, 36 minus 4. I think I get 32 here. And plugging in a 3 and 2, it's 27. I think I get 21. I think I did that right. I think I did that right. So I got the answer. Here I go. I'm doing this formula. I've got 32 times x minus, now remember the x naught, y naught, z naught was the point. And the point is right there, 3, 2, 42. So x minus 3. Here comes the fy is a 21. This is my normal vector, 32, 21. I mean, I didn't even write it as a vector, sorry. My 3D gradient is 32, 21, -1, right? 32, 21, -1. And I'm using it here for my formula. Y minus 2, and then the z, -1, times the z minus 42. That's the equation of the tangent plane at this point. That's pretty cool. That's pretty cool. I'm going to clean it up. Distribute the 32. I'll clean it. I like you to clean it up too, but this is just second grade stuff here. Man, it's kind of interesting. Those 42s cancel. The 96 I like to put on the other side. So I think I got 32x plus 21y minus z equals 96, I think. That's the equation of my tangent plane. Using this cool formula. And using this new concept of a 3D gradient. It's weird. I'm glad you got it, though. I think I explained it well. I'm taking a 3D surface, and I'm moving the z over, and it's still a 3D surface, but I'm renaming it and calculating this new 3D gradient. Yep. That's normal to the surface. It's normal to the surface. That vector is normal to the surface. That's why it works good. I mean, that's why it's normal to my tangent plane. That's why I need it for my tangent plane. It's normal to the surface, so it works great for my tangent plane, right? Yeah, that's awesome. That's it. That's really kind of all. I mean, that's 13.7. I could do another problem and see how, but I think you get the idea. We could try one more here. Let's try one more. Oh, I was going to say this. The other thing the book asks, I'm not as interested in, so I found the equation of the tangent plane. They also say, let's find the equation of a normal line. Well, what do they mean by that? Well, so at this point, I can come up with a normal line. That means a line that's normal to the surface. A line, an infinite line that's normal to the surface. Well, if you remember from chapter 11, the equation of a line in space was given as parametric equations. What we needed was a point that's on that line, which is the point 3, 2, 42. And if you remember the parametric equations of a line, then I also needed a parallel vector to my line. What would be a good parallel vector to my line? That 3D gradient vector, that gradient vector I just used is parallel to my normal line, which is normal to the surface. So now I'm going to write, where is that? Oh, there it is. I'm going to write plus 32t plus 21t minus 1t. Remember lines? Remember lines? You needed a point and a parallel vector to your line. This is the equation of a normal line to a surface. Not as, I mean, I don't know. I don't see how useful that is. I like the tangent plane. Not sure how useful that is, but I like the tangent plane. Not as interested in the normal line, but the book might ask for it, and I might even ask for it. I guess I might have seen it on some of my take-home stuff or whatever. I might have seen that. Let's do another one for fun. Just look at this guy. I mean, that's a mess. Let's pretend I'm at the point. Oh my God. Let's pretend I'm at the point. Okay, I think I'm at that point. 1, 5/3, -1. I think I'm at that point. So I'm at that point. I'm on this 3D surface. It is a 3D surface. There's only 3 variables there. There's not 4 variables there. There's 3 variables there. It's a 3D surface of some kind. I'm at this point, and I want the equation of the tangent plane. I want the equation of the tangent plane. Well, so we've done this already once. We'll just do it this again, I guess. I need big F. How do I get big F? Sure, get everything on one side equal to 0. Exactly. So if I get everything on one side equal to 0, you said the best way would be to move him over here. I think I agree with that. So this is 5z cubed x minus x squared yz, I just put it there, plus a 2y. So when I get it all on one side, it does equal 0, but I'm going to call that big F. And then I need big Fx, big Fy, and big Fz. Right, that's all. This might not even be worth doing. I don't know. Let's try it, I guess. Big Fx, big Fx. 5z cubed. With respect to x, negative 2xyz. And then nothing. Okay. All right, with respect to y. With respect to y, that's a nothing. That's a negative x squared z, and that's a plus 2. With respect to z, it's 15 z squared x minus x squared y. Cool, that's it. I need to evaluate all these at the point. That's a little tedious, but that's what I got to do. I got to evaluate these at the point. So then the fx becomes, when you plug in that point, 1, oh wait, negative 1 for z. That's a negative 5 minus, that's a negative 1, that's a 5/3, that's a 1, that's a 2, that's a 10/3, I guess. Positive 10/3, maybe. Positive 10/3. Right, negative 15/3 plus 10/3, that's negative 5/3, I think. I don't know. When x is 1 and z is negative 1, shouldn't be too hard, but it's just a 1, I guess. 1 plus 2 is 3. All right, cool. And then z is a negative 1, x is a 1, that's 15, minus, that's a 1, but that's a good old 5/3, so 15 minus 5/3. Okay, get a common denominator and multiply by 3. That's 45 minus 5. That's 40/3. Okay. All right, there it is. That's my 3D vector. And, of course, I use it just like I did to get the equation of the tangent plane. Yeah, the tangent plane is... where are we? Negative 5/3 times x minus the x point, which was a 1. A positive 3 times y minus the y point, which was a 5/3. And then a plus 40/3, if I did all that math right, times z minus the negative 1, or z plus 1, equals 0. I do like you to clean that up, but I don't think I will today. I'll just leave it like that.
Is there a symbol for the tangent plane? Like there is for...
No, it's a plane. So it's just the good old equation of a plane. This is, and the good old equation of a plane had a normal vector, A, B, C. But if it's a tangent plane, then that normal vector is kind of specifically big Fx, big Fy, big Fz. But it's just, you could, I had it up there a minute ago, in general, you could call it, right, this is the equation of the tangent plane, right? There's no symbol other than that's its equation, right? Just the word tangent plane. Well, I'm good. I'm happy. I might want to quit today. So I eased into 13.7. It's not a big deal. It's just the tangent plane. It's not hard. What was a little difficult was me trying to explain this big F notation, but you guys seem to get it okay. So cool, I think we're cool. And to try to explain why does this 3D vector become normal to the surface. So I tried to explain that, but whether you, right, so that was cool. So I think we'll quit today. You know, what's coming next week, there's just a couple more sections, a 13.8, a 13.9, and it's kind of finding maxes and mins in 3D world. And then what it is actually it's finding maxes and mins in 3D world, and then it's word problems finding maxes and mins in 3D world. So it's, yeah, so it's max, min, math problems, and then some good word problems. So that's how this chapter kind of ends. So we can do that next week and be ready for a test the following Monday. But we'll try a little quiz this Monday. It won't have a tangent plane on it. It won't have, but it'll have any of this stuff on it. So cool. All right, I'll quit today. I'll hit pause, and I'll see you guys Monday.